Okay, hello everybody. So in today's video, I will be teaching you how to hybridize for the polyatomic cation IF6 plus. Now, of course, in case you need a little bit of a refresher, a cation means you are losing the electron. You have a plus charge on your molecule. So if you look up here, you will see that we do have a 1 plus molecule, meaning that it is a cation. Be losing that electron, and that'll come in a little more handy later on when we actually start to draw our Lewis structure diagram. For now, I'd like you to take a look at the steps we will be going through. It is only a 4-step process, so it is not too difficult, but these are the steps we will be going through in order to solve for the hybridization of IF6 1+. Step 1, draw your Lewis dot diagram. Step 2, condensed electron configuration. Step 3, draw your energy level diagram. And step 4, of course, your actual hybridization. So, before we get into the actual solving of the polyatomic cation of IF6 1+, let's go over a few different types of bonds you will commonly see when solving these VSEPR and hybridization problems. The first type of bond is the covalent bonds. This is when two nonmetals, so nonmetal number 1 and nonmetal number 2, come together and agree that they should share electrons, like this one and this one, in order for them to both have a full valence electron shell. So they agree, they share their electrons, and it eventually happens like this. They share the electron, and now they both theoretically have a full valence electron shell. Next, we have our coordinate bonds. This is when one of the nonmetals is sharing both of their electrons to the other one, so that they could both have a full valence electron shell. It's essentially like working in a group project, right? You're partnered with one of your friends, and he doesn't want to do any of the work, but he's still your friend, so you both want to get good marks. So what do? You offer to do both your slides and his slides. And in the end of the day, you both get good marks and you're both happy, but you had to do a little bit more work. So, same case here. Atom number 1 gives both the electrons, whereas the atom number 2 gives really nothing. It's just there to have a full valence electron and get a free 90 on its assignment. So, there we go. In our case, we will not be seeing any bonds in the molecule IF6 1+. However, we'll definitely see this in a lot of other molecules in VSEPR hybridization. Lone pairs. This is when the central atom has a lone pair of electrons attached to it. It doesn't participate in any reactions, however, it plays a crucial role when it comes to identifying the geometry of the actual molecule. For example, let's take a look at water. Water is a very common, and of course it is a tetrahedral molecule. These two lone pairs play a big role when it comes to discovering what the angle and the geometry of the actual is. However, it has nothing to do with the actual reactions. Next, we have resonance structures. Resonance structures are essentially a different way of drawing or writing the same molecule because it has a bond greater than a single bond. For example, double bond or triple bond. For example, A double bonded to X, single bonded to X, can also be written as A double bond this X, this X. Resonance structures. Okay, so now that we went over a few of the basic ideas that you need to understand before actually getting into the hybridization and VSEPR problems, let's take a look back at our instructions manual here, our four-step process to solving hybridization problems. So let's get started with step number 1, drawing the Lewis dot structure. To begin with our Lewis dot diagram, let's start by drawing our central atom and the surrounding atoms around it. So in this case, we know that our iodine is our central atom. So We draw it in the middle. And then our 6 fluorines will be the surrounding atoms. So we're going to draw 6 fluorines. 1, 2, 3, 4, 5, 6. Now we need to figure out what to do with the valence electrons and what the bonds are like between each fluorine and the central atom iodine. Now typically we would use our need-have method. However, in this case, if you look at where iodine and fluorine are in the periodic table, so iodine is in group 17, so it has 7 valence electrons, and fluorine is also in group 17. So it also has 7 valence electrons. Technically, from what we've been learning, fluorine and iodine only need 1 more electron to be happy, to be stable, and have that full octet, that full 8 valence electron shell. However, we not only have 1 fluorine in this molecule, we have 6. So you're probably wondering, how in the world is iodine going to be able to hold up 6 fluorines when all it needs is technically 1 electron, and each fluorine has 1 to offer? Well, it's a special type of molecule, and in this case we call it a non-octet molecule. It does not follow that octet rule. So iodine can actually have more than 8 valence electrons. And we know whenever we have a non-octet molecule, all of the bonds between the surrounding atoms and the central atoms are going to be single bonds. So 1, 2, 3, 4, 5, 6. Single bonds. Now we still need to refer back to our need-have method in order to find out how many electrons are left after we put all of these single bonds in place. Now, in order to find out how many electrons we have left so that we can put them around our fluorine atoms here, we need to find out how many electrons we had and subtract the amount of electrons that are being used within each of these single bonds. Remember, one single bond accounts for 2 electrons being used. So if we count the amount of single bonds, 1, 2, 3, 4, 5, 6, 6 single bonds. Each single bond has 2 electrons, so 6 times 2 equals 12. 12 electrons are being used within the single bonds. So we're going to find out how much we had, which is fluorine is in group 17, so it had 7 valence electrons. We have 6 fluorines, 7 times 6, plus iodine, which is also in group 17, so it has 7 valence electrons. And that equals 49 electrons. However, be careful, because remember this 1 plus charge, that means we lost an electron. There is minus 1 electron in this molecule. So, realistically, we have 48 electrons, because 49 minus 1 electron equals 48 electrons. So we had total of 48 electrons. We are currently using 12 of those electrons within the single bonds. So how many do we have left just floating around our fluorine atoms? Well, it is 48 minus 12, which equals 36 electrons. So now knowing that we have 36 electrons left to use and place around our fluorine atoms, we can start placing them one by one until we have none left. 35, 36, and would you look at that? Perfect. We filled out every single fluorine atom, and we do not have any leftover electrons to place on the central atom to be lone pairs. So we don't have any lone pairs in this case. It works out perfectly. The final step of this process would be to add brackets around our Lewis dot diagram with a little +1 symbol at the top right corner to indicate that we did in fact take out an electron in this Lewis dot diagram due to the charge that IF6 has. 1 plus charge. Now we move on to the next step of hybridization, which in this case is electron configuration. A short review as to what electron configuration is there's a total of 4 orbitals, and each row on the periodic table represents a level. The lower on the periodic table you go, the higher the level gets. It's almost like an upside down elevator. So, group 1 and 2 represent your s orbitals. Group 3 to 12 represent your d orbitals. And group 13 to 18 represent your p orbitals. Lastly, we have your f orbitals, which are the specialer ones because these are the elements that have been chopped out of the periodic table and put underneath. When finding the electron configuration for an element, we start at the top left corner at hydrogen, and we read left to right and work our way down, almost like reading a book. In addition, for every orbital we pass in a specific energy level, we have to note that down, and we also have to write a superscript the amount of atoms we passed within the orbital. I'll show you what that looks like in just a second. Let's try do the electron configuration for lithium. Let's start at the top left corner at hydrogen. So, remember, with electron configuration, helium is considered to be an s orbital, essentially filling in this spot right there. So if we were to solve for lithium, we'd start at the top left corner. S orbital is in level 1. Pass 2 electrons within the s orbital, so we'll put that as a superscript, and then work our way down. We hit lithium. Lithium is in level 2, is in an s orbital. However, we only had to get through 1 atom to get to lithium, but 1. It gets slightly more confusing when we get to the d orbitals, because now the energy level changes every time we enter into the d orbital. For example, let's do iron. Iron is in energy level 4 as it says here. However, that is not the case with d orbitals. D orbitals, it is always 1 energy level below what it actually says. So in this case, if iron is in an energy level 4, it's 1 less because it's d orbital, so it'd be energy level 3. And we pass how many atoms in order to hit iron? 1, 2, 3, 4, 5, 6. 6 electrons, so we put that as a superscript. Now it gets a lot more tedious when we're writing the electron configuration for elements much higher on the periodic table. For example, iodine, the one we will be doing. Because it is so high, we will have to pass every single orbital and note down every single energy level that we pass before getting to actual iodine. To avoid this annoying process, we came up with a shorter and more quicker way of doing electron configuration called shorthand electron configuration. This is where we look at the first noble gas we passed before we got to iodine, which in this case is krypton, and we just write it at the very start of our electron configuration just like this. And we continue the electron configuration from there. So let's do iodine. Krypton, then we move down to energy level 5, s orbital, pass 2 atoms, put superscript 2. Then we get to the d orbital. Remember, d orbital is always 1 less energy level than what it says. So if it says 5, it's actually 4. 4 d orbital, and we pass 10 d atoms, before we get to the p orbital. So 10 as a superscript, and then we reach the p orbital. P orbital, there is no exception, so it is just how you see it. Energy level 5, p orbital, and we get to 1, 2, 3, 4, 5 atoms before we hit iodine. So we put 5 as a superscript. However, be careful, because remember that IF6 has a charge of 1+. So that affects our electron configuration. Because we lost an electron, we're going to subtract 1 from our final p orbital superscript. So it'll actually be 5p4. And just like that, we have your condensed electron configuration for iodine. Now, moving on to step 3 of the process for hybridization of IF6 1+, energy level diagrams. Energy level diagrams are essentially a chart that show a visual representation and comparison of orbitals and their energy level. Important thing to note before we get started with this diagram is that earlier I would refer to the superscript, the electron configuration, as atoms. However, they actually represent electrons, the amount of electrons within the type of orbital. Each type of orbital has a specific amount of orbitals within it. So, for example, the S-type orbitals can have up to 1 orbital, P-type orbitals can have up to 3 orbitals, and D-type orbitals can have up to 5. Each single orbital can hold up to 2 electrons. For starters, we need to write down all the orbitals we have along with their energy levels within their given category. But before we do that, we need to write the krypton element, the s orbital, to indicate that we've already accounted for all the other orbitals and energy levels before this noble gas. So now we can begin placing the orbitals that we have in our electron configuration in their given category. So 5s2 belongs the S category. Don't worry about the superscript for now or the amount of electrons each orbital has. We'll do that later. 4d10, 4d belongs in the D category. We're going to place that slightly higher above 5s because D orbitals are the strongest in these three. D orbitals are second strongest and S orbitals are the weakest. 4d, 5 orbitals represent D. And lastly, we have 5p. 5p. The reason 5p is above the 4d, even though the d orbitals are stronger than p, is because the p is a higher energy level than d. Now we can look back down at the superscript of the iodine electron configuration to find out how many electrons belong in each orbital. But before we do that, we must remind ourselves of a few rules. Alboff's principle, the lowest energy orbitals must be filled first. Hund's rule, multiple orbitals are equal energy. Each orbital must get a single electron before being paired up. And Pauli's exclusion principle, which is 2 electrons placed within the same orbital will spin in opposite directions, and that will be indicated by the direction of the half arrows that we draw. So now we can begin to fill out these orbitals. We have 5s2, 2 electrons. First one spins up, second one spins down. 4d10, 10 electrons within the d orbital. 2. And 5p4, 4 electrons within the p orbital. Now it's always important to remember that the electron configuration in the 5p orbital looks like this because we do have that 1 plus charge. If that 1 plus charge was not there, we would have 1 additional electron. However, it is there. So we need to make sure we do not make that mistake of putting 1 extra electron. And just like that, we now have our energy level diagram. Now we move on to the final step of hybridization, the actual hybridization part. This is where all 3 previous steps will come into play. Now, I could just sit here and tell you how to do the hybridization because it's not a hard process, but what's the point in telling you how to do it if you don't know why you're doing it? So, let's explain it a little bit. Well, hybridization is essentially when atomic orbitals come together to form hybrid orbitals, hence the word hybridization. Well, you're probably wondering, why do we need hybridization, Peter? What's its use? Well, there's a bit of an older theory called valence bond theory, and this theory is used to explain the covalent bond formation in many molecules. But the key word here is many molecules, not all molecules. For those molecules that do not fall under the VBT, valence bond theory, we like to use what's called hybridization to explain how these covalent bond formations work. Okay, so now that you understand it a little better, let's try an example of hybridization. So let's do sp 3. sp3 is a combination of one s orbital and p orbitals. Let's do another one. So sp2. This is a combination of one s orbital and two p orbitals. Nope, sorry, I put that as 3's instead of. So as you can see, two orbitals come together, form hybrid. So to find out what kind of hybrid orbital we have, we first need to identify the types of bonds found in our Lewis structure all the way back in step 1. So if you take a look at our Lewis structure, all we see is single bonds. However, in hybridization, we no longer refer to them as single bonds, we call them sigma bonds. And there's an easier way of writing sigma out. There's actually a symbol for it. And it kind of looks like a triangle, the instrument nobody plays in band class. Below our arrow with hybridization on it, we are going to write out the amounts of bonds we see and the types of bonds we see within our molecule. In this case, all we have and see is sigma bonds, 6 of them. So we're going to write out 6 sigma bonds. Now what you're going to do is you're going to want to draw a new diagram, much like the one we drew for our energy level diagram. And this diagram is what's going to show how the two orbitals in the highest energy level average out in order to form a hybrid orbital. Next, you're going to want to put a orbital line for each type of bond you see, or for the amount of bonds you see. So in this case, we have a total of 6 bonds, meaning we're going to have a total of 6 lines. Now in hybridization, we represent sigma bonds as 1 electron. Lone pairs represent 2 electrons, and coordinate covalent bonds also represent 2 electrons. But in this case, all we have is sigma bonds. So for all 6 of these lines, we are going to fill it up with 1 electron. Now finally, all we have left to do is to name the actual hybrid orbital. So what we're going to do is, best way and easiest way to do this is through a checklist. We write a S has 1 orbital, P has 3 orbitals, D has 5 orbitals, and if you wanted to, you could write F. It has 7. It goes up by increments of 2 odd numbers. However, we do not even hit the F section. We only go up to D. In this case, you look at how many bonds you have, and for each bond, you put a check in one of the spaces. So, we have 6. 1, 2, 3, 4, 5, 6. We can finally name our hybrid orbital. We have 1 S. We have 3 P's, so P3. And we have 2 filled out in the D's, so D2. Lastly, it is always a good idea to circle all of your bonds, coordinate covalent bonds, or lone pairs that you have within a molecule so that you can easily identify them later on when you actually do the hybridization. Overall, this is our new hybrid orbital. So now let's get into a bit of detail as to what intramolecular forces and intermolecular forces are, starting with intramolecular forces. These are the forces that are found within the actual molecule. They influence the chemical properties of the molecule, and they consist of ionic bonds and covalent bonds. They are essentially the sticky glue of the actual molecule. It's what holds the molecule together. So if we take a look at an example like water, we can see that the intramolecular forces in water, H2O, are covalent bonds. 2 of them. That is exactly what is holding this water molecule as a whole together. Which brings us to the next type of force, which is intermolecular forces. These are the forces between molecules. So now we are no longer within the molecule, we are outside of the molecule. These are the forces holding 2 molecules together. They influence the physical properties of a substance, and they consist of dipole-dipole bonds, hydrogen bonds, and London dispersion forces. Now, if we take our example of water once again, for intermolecular forces, we can see that these two water molecules will be held together via hydrogen bonds. Water is another one of those examples that carry dipole-dipole forces. This is because water as a molecule is polar. Hydrogen and oxygen create an electronegativity difference greater than 0.4, and as a result, one side of the molecule is positive and the other one is negative. This means that when it bonds with other water molecules, there is a slight attraction, the same way there's an attraction with magnets, negative and positive. Along with that, water, of course, along with every other molecule, really has London dispersion forces. Now, let's take a look at the molecule that we had, IF6 1+. So let's analyze and discover what kind of forces we have going on here, both intermolecular and intramolecular forces. So as for intramolecular forces, we can see that we have covalent bonds. Now, as for the intermolecular forces, we can see that if we had IF6 1+ go near or bond with something that had a negative charge, they would actually be attracted. There would be a force attraction between them because opposite charges attract. Now, one physical property that IF6 1+ will have is it will actually have quite the high boiling point, actually a very high boiling point, because it's a very polar molecule. This is because the electronegativity difference between the F and the I, the fluorine and the iodine, is so high, and it's above average, and as a result, when bonded with other molecules, it'll take a lot of heat in order to break those intermolecular forces. Lastly, one very important physical property that IF6 1+ has is that it is soluble in water. This is because hydrogen bonds love forming bonds with H and N, H and O, and H and F. And conveniently enough, IF6 has a lot of F's, so it is very soluble within water.